This is Chapter 2, Refrigeration Fundamentals, presented by RSCS, and this is a program that I've been using for years to help students that take the NATE exam, which stands for North American Testing, and what this basically, excellence I should say, and what this is, it's an exam that basically tests your competency as a refrigeration air conditioning mechanic. It's divided up into different areas and there's different levels, and I will tell you this, if you decide to pursue this NATE certification, what is nice about it is basically it gives you a leg up as far as getting a job out in the field. So something you might want to think about. Talk about basic system components. Ideal refrigeration cycle, refrigerants, refrigerant oils, leak detection, and commercial refrigeration systems. Basic system components, there are 5 different components that make up every vapor refrigeration system: refrigerant, evaporator, condenser, compressor, metering device. All these components on the next slide must work together in order for the system to produce a refrigeration effect. Their size and configuration can vary from a system to systems, but their function is always going to remain the same. From a very small system as a typical household refrigerator to a large industrial refrigeration system, they all have the same 5 basic components. In this slide here you have the basic components of any refrigeration air conditioning system. You have the compressor, discharge line to the condenser, where the condenser takes the heat that was pulled out in the evaporator and releases it to the ambient, and the refrigerant changes from a high pressure vapor to a high pressure liquid. Liquid line over here, and that feeds into the metering device, and in this metering device is I'm going to assume this is a thermal expansion valve, although it's not well illustrated. Here you have a distributor indicating that this evaporator coil has more than one circuit. So we're feeding into 5 different circuits of this evaporator coil. Of course, evaporator coil is going to have a fan behind it. It's going to suck the air from the room or the cabinet, and in the process of doing it, that warm air is going to have the humidity removed, and the result is low pressure suction vapor going to the compressor. As I said in previous presentations, the purpose of a compressor is to pump vapor, not liquid. None of these refrigeration systems we're going to talk about pump liquid in any way, shape, or form. Basic system components, if there's a problem with any one of those components, if it's not sized correctly, it's not operating correctly, it'll cause a problem that will affect the entire system. Understanding how these 5 components operate, how they work together in a basic building block for designing, installing, and repairing the majority of refrigeration systems in use today. Basic system components, a closer look at the 5 system components. Refrigerant is the lifeblood of a system. It is the fluid that flows through the other 4 major components. It first absorbs heat energy from the product or space to be refrigerated, thus cooling them. The absence of heat is cold, and then releases it somewhere else to an area where it does not matter. Think of refrigerant as a heat sponge that can soak up heat energy, then release that same heat energy elsewhere at the appropriate time. Evaporator is a heat exchanger between the product to be refrigerated and the refrigerant. In the evaporator, the liquid refrigerant absorbs heat energy from the product to be cool and reduces the product temperature in the process. As the liquid refrigerant absorbs the heat energy, it changes state from a liquid form to a vapor form. The condenser is also a heat exchanger. However, this time the refrigerant gives up its absorbed heat energy, releasing it to another area where it is wanted and where it does not matter. And during this process, the refrigerant is changed back into a liquid form. The compressor is a vapor pump that acts as the heart of the refrigeration system. Without the pump, nothing happens. Pressurize the refrigerant to a level that allows it to absorb and release heat energy at the appropriate temperatures for its application. while at the same time creating a pressure difference required to circulate the refrigerant through the system. The function of a metering device is to control the flow meter of the correct amount of liquid refrigerant into the evaporator. The amount and rate of refrigerant entering the evaporator is an important aspect of the overall operation of this system. Putting the 5 components together, let's take a look at how these 5 components are combined to make up a complete system. The outlet of the compressor is connected to the inlet of the condenser. The refrigerant line connecting the 2 components is called the discharge line. The outlet of the condenser connected to the inlet of the metering device. The refrigerant line connecting 2 components is called the liquid line. The outlet of the metering device is connected to the inlet of the evaporator. If the metering device is installed right at the inlet of the evaporator, there is no interconnecting refrigerant line used. However, some systems, including a distributor and feeder tubes between the metering device and the evaporator. Outlet of the evaporator is connected to the inlet of the compressor. The refrigerant line connecting these 2 components is called the suction line. The size and shape of the components and the distance between them will vary from system to system, but in the order of operation, how the refrigerant flows from the compressor to the condenser to the metering device or to the evaporator and back to the compressor is the same for every vapor compression system in operation today. The following slides describe what happens to the refrigerant as it travels from component to component. The basic vapor compression refrigeration cycle is a closed loop system. That is, the process that is continuously as long as the system is running. The same refrigerant continues to circulate throughout the system. It will not wear out. I want to make it very perfectly clear. There are people out there who tell you you have to change the refrigerant because it wears out. That is not true. Refrigerant never wears out. As long as the system is leak-free, the refrigerant can be used over and over and over again for many years. I have seen refrigeration systems work in excess of 40 years without any problems. An explanation of the refrigeration cycle can start at any point in the system. Since it's a closed-loop system, the end of one part of the process, the beginning of the other. Let's start our explanation with the inlet of the compressor. Refrigerant enters the compressor as a low pressure, low temperature vapor. It initially flows into the cylinder with a relatively large volume. As shown in figure 2-2 in the next slide, refrigerant vapor is compressed as the volume of the cylinder is reduced. Decrease in volume causes an increase in both the pressure and the temperature of the refrigerant. The refrigerant is discharged from the compressor into the discharge line as a high pressure, high temperature vapor. In this illustration here, we have a reciprocating compressor over here. Notice that you have intake or suction valve on this side from the suction line, and we have an exhaust valve going to the discharge line. Piston moves up and down. As the piston draws down, intake valve opens up as the stroke furthers down, and of course this is connected to a connecting rod and then to a crankshaft down here. Once the piston hits bottom dead center, then it starts its travel up, and by traveling up, the intake valve or suction valve is shut, the discharge or the exhaust valve is open, and now the refrigerant pressure and temperature has increased in the process of this cycle. And this is your top dead center. This is as far as the piston travels in a forward mode. As the high pressure, high temperature refrigerant vapor enters the condenser, it starts to give up or reject some of the heat energy into a cooling medium, usually air or water passing over or through the condenser. And look at figure 2-3 on the next slide. As the heat energy is transferred from the refrigerant to the cooling medium, the temperature of refrigerant vapor is reduced. The drop in temperature is called de-superheating. We are removing superheat, causing the vapor to condense into a liquid. As the liquid continues to reject heat, it becomes subcooled. The liquid refrigerant exits the condenser and is sent to the metering device through the liquid line. Okay, on the condenser, this is an air-cooled condenser. Notice we have cool air surrounding this condenser. Basically, we have hot refrigerant vapor coming from the compressor here. And of course, as that high pressure, high temperature refrigerant circulates through these tubes, it gives up its temperature to the surrounding cooler air. And by doing that, the refrigerant changes from a high pressure, high temperature vapor to a high pressure liquid, leaving this condenser. A metering device which controls the flow of refrigerant to the evaporator consists of a calibrated orifice, a small hole in which the refrigerant liquid is forced. This restriction reduces the pressure of the refrigerant, decreases the pressure, which also causes a decrease in the temperature of the refrigerant. As the pressure is reduced, a small portion of the refrigerant flashes off from liquid into vapor. Heat energy is removed from the remaining liquid refrigerant and further reduces its temperature. The refrigerant exits the metering device at a lower pressure, lower temperature, and as a liquid/vapor mixture. The refrigerant is now a mixture of both vapor and liquid saturated entering the evaporator coil. And look at figure 2-4 on the next slide. The mixture is made up of 75% liquid and 25% vapor. The actual percentages will actually vary depending on the system design and the operating condition. In order for the remaining portion of the liquid refrigerant to change from a liquid state to a vapor state to evaporate, in this case, heat energy must be added to the refrigerant. No heat, no change of state. Okay, in this figure 2-4, you have the evaporator section here, and notice that we're utilizing for our pressure drop, the metering device. This is a solid column of liquid entering the thermal expansion valve. The refrigerant enters the evaporator coil as a mixture of liquid and vapor, 75 to 25% ratio, I believe the previous slide talked about. And as heat is picked up from the food product or from the surrounding air, the absence of heat is cold in the process. We also drop the dew point as well as the humidity, and by doing that we actually remove moisture from the box or the space that we are cooling if it's an air conditioning application. Warm air in, cool air out, simple as that. And notice on the TXV you've got the sensing bulb always located on the outlet side. Something I'm going to say right now so you don't forget this. On the suction line, the TXV bulb must be mounted horizontally, not vertically. I have actually seen in places where the bulb was installed improperly on a vertical rise, or not insulated properly, or worse yet, the bulb not secured, and we've had major problems with the air conditioning refrigeration system. The heat energy comes from the product to be cooled. The refrigerant continues to absorb heat energy until it is changed completely into vapor. As the vapor continues to absorb additional heat, it becomes superheated vapor. Refrigerant leaving the evaporator in all vapor state and returns through the suction line to the compressor, where the process will begin all over again. Okay, the complete process. If you look at this diagram here, you can review the different components that we talked about. Of course, the heart of the unit, which is the compressor, the suction line, discharge line. We hook up to the condenser coil, and the condenser, remember, takes this high pressure, high temperature refrigerant vapor from the compressor and gives up the heat that was absorbed in the evaporator in the condenser side. The absence of the heat in the refrigerant cools down the refrigerant into a liquid state, and by going into a liquid state, Now we go into the metering device. In this case, this is a TXV. And from here, we have created a pressure drop, and we have a mixture of liquid, low pressure liquid, and vapor into the evaporator coil. And of course, we have a fan, evaporator fan, which is going to take and pull the heat through this coil, and the heat will be absorbed by the refrigerant. And in doing so, the refrigerant changes from a liquid, low pressure liquid, to a low pressure vapor only. And then of course this vapor exits the evaporator coil, goes through the suction line back to the compressor, where this process starts all over again. Please remember, compressors are designed to do what? Only pump vapor, not liquid. Okay, complete process. Start the compressor, and notice the refrigerant leaves the compressor at a high pressure, high temperature vapor when the refrigerant exists at all vapor state. The temperature is higher than its saturation point. It's commonly referred to as superheated. From the compressor, the refrigerant flows into the condenser, where it releases energy. In doing so, the refrigerant changes or condenses from a vapor to a liquid. The liquid refrigerant is still at high pressure, but at its temperature it's now lower than its saturation point, and therefore we refer to this as subcooled liquid. Subcooled refrigerant leaves the condenser, all liquid state, and enters the metering device. I might point out the liquid line should be 100% liquid. Shouldn't be no flash gas taking place in there. If there is, that means some of the refrigerants boiled off and there's a problem. The job of the metering device is to create a pressure drop of the refrigerant and meter the correct amount of refrigerant into the evaporator. As its pressure is reduced, some of the refrigerant changes from a liquid to a vapor. The temperature of the refrigerant is also reduced, and it exits the metering device as a saturated mixture of vapor and liquid. The low pressure, low temperature, saturated refrigerant now enters the evaporator coil, where it absorbs a sufficient amount of heat energy to boil into a vapor or evaporate. The refrigerant leaves the evaporator as a superheated vapor, returns to the compressor, and the cycle is repeated again. As long as the compressor is in operation, the refrigerant will flow from component to component in a continuous loop until satisfied. An ideal refrigeration cycle, using R134A as an example. Examine the different pressures, temperatures, and states of the refrigerant may undergo during an ideal cycle. Notice what we have coming into the suction line. We have 18 psig at 30 degrees Fahrenheit. Leaving the compressor, it has been elevated to 134 psig. Look what happens to the temperature. It goes up to 145 degrees. Discharge line enters the condenser at 134 psig at 105 degrees design temperature. Then that refrigerant course turns into a liquid. Notice that the pressure is still pretty much the same as up here. Well, look what happens to the temperature. It drops to 95. We're back down into a liquid state. We enter the metering device coming up here at 134 psig, which is the same as a condenser, 95 degrees Fahrenheit on the liquid line. And then of course we leave this pressure drop or metering device at 18 psig, and the temperature drops off dramatically. And in this illustration we can show you the difference between vapor, liquid, and a mixture of vapor and liquid in this illustration. Starting at the outlet of the compressor, we assume that the pressure of the refrigerant vapor is 134 degrees psig and the temperature is 145 degrees Fahrenheit. Refrigerant travels from the compressor through the discharge line to the condenser and enters the condenser at the same pressure and temperature, 134 psig and 145 degrees Fahrenheit. The refrigerant now starts to transfer its heat energy to cooler medium, air or water, passing over or through the condenser. Temperature of the refrigerant will be reduced to its saturation temperature. Because of the relationship between the pressure and temperature for a saturated refrigerant is constant and predictable, you can refer to as a pressure temperature PT chart to find the saturation temperature of the refrigerant at a given pressure. Table 2-1 on the next slide shows an excerpt from a PT chart for R134 alpha. As you can see from the dotted green arrow, the saturation temperature 134A at 134 psig is approximately 105 degrees Fahrenheit. So here's the PT chart. Notice here if you got the arrow, notice that at 18.4 psig, the actual saturation temperature of the refrigerant is 20 degrees. Now we go down here at about 134, which we saw in that previous slide. 130, we don't have 134, so we're going to interpolate, go between these two, and basically look what happens to the temperature of the saturation temperature of the refrigerant at this point. Down to 100, it's at 104 degrees Fahrenheit. As heat energy continues to be removed from the saturated refrigerant, its pressure will remain constant at 134 degrees, 134 psig, and its temperature will remain constant at 105 degrees Fahrenheit. However, the removal of heat energy causes the state of the refrigerant to change. That is, the vapor begins to condense into a liquid. Once enough heat energy has been removed for all of the vapor to be condensed into liquid, any further removal of the heat energy will cause the temperature of the liquid refrigerant to drop. Let's assume that enough heat energy is removed from the liquid refrigerant to drop its temperature or subcool it another 10 degrees to 95 degrees Fahrenheit. The refrigerant leaving the condenser of the liquid is at a pressure of 134 psig and a temperature of 95 degrees Fahrenheit. Note so far that the pressure of the refrigerant has remained the same. From the condenser, the refrigerant flows through the liquid line and into the metering device. At 95 degrees Fahrenheit, liquid refrigerant enters the metering device. It is forced through a small orifice and the pressure is reduced from 134 psig to 18 psig. This sudden reduction in pressure caused a portion of the liquid to literally flash off or vaporize from liquid to vapor. That explains the percentage of 75% liquid, 25% vapor. The temperature of the refrigerant also drops dramatically to 20 degrees Fahrenheit. And it says refer back to 2-1 and look at the dotted arrow. Saturated refrigerant enters the evaporator at a pressure of 18 psig and a temperature of 20 degrees Fahrenheit. As the refrigerant flows through the evaporator, it absorbs heat energy from the product to be cooled. The heat energy causes the rest of the liquid portion of the saturated refrigerant to evaporate into a vapor form. Once all the liquid has been changed to vapor, any additional heat energy absorbed by the refrigerant will cause the temperature of the refrigerant to increase. Let's assume that enough heat energy is absorbed by the refrigerant vapor to raise its temperature or superheat it another 10 degrees Fahrenheit. The temperature of the refrigerant leaving the evaporator is now 30 degrees Fahrenheit. The pressure remains at 18 psig. Refrigerant vapor travels through the suction line to the inlet of the compressor. Once again, the compressor is only designed to pump vapor, not liquid. Enters the compressor at still a pressure of 18 psig and a temperature of 30 degrees Fahrenheit. The compressor will then compress the refrigerant vapor, decreasing its volume and increasing its pressure to 134 psig on the discharge side. This increase in pressure means that the temperature also increases back to 145 degrees Fahrenheit and the cycle starts all over again. Pressure losses. In an ideal refrigeration cycle, there are only two pressures within a system, the low side pressure and the high side pressure. In reality, however, this is not always the case in many refrigeration systems. Long pipe runs, large evaporators, and condensers create pressure losses within a system. The friction generated by the refrigerant as it travels through the lines and components also causes its pressure to drop. Pressure of the refrigerant vapor when it leaves the evaporator may not be the same as when it enters the compressor. The pressure of the liquid refrigerant when it leaves the condenser may not be the same as when it enters the metering device. For large evaporators, the pressure at the outlet may be less than in the inlet. The same may be true for larger condensers. The pressures at the outlet may be lower than at the inlet. As a technician, you need to be aware of these pressure losses and take them into account when you are servicing the system. Temperature gains and losses. Not only can the pressure change as the refrigerant travels through the discharge liquid and suction lines, but also its temperature. The temperature of the refrigerant vapor in the suction line may increase or decrease on its way back to the compressor. If the suction line passes through an area with high ambient temperature, the heat from the ambient air will be absorbed by the refrigerant vapor in the suction line and cause its temperature to rise. To minimize temperature gains, the suction line is normally insulated. The temperature of the liquid refrigerant in the liquid line may also increase or decrease depending on the ambient temperature of the area through which the line is run. The liquid line is normally not insulated, but that's changing according to the new Title 24 regulations. In the future, you will see both the suction line as well as the liquid line insulated. We're exposed to the ambient. Since the ambient temperature is typically lower than the liquid line temperature, but if there should be a severe temperature gains, it'll cause problems for the system. Rating refrigeration equipment. Refrigeration air conditioning equipment is rated by how much heat energy it can remove from a product or an area within a specific time. Components are typically rated in BTUs per hour, BTUH, or BTUs per hour. As an example, system rated at 20,000 BTUs can remove 20,000 BTUs of heat energy for each hour that it operates. If a system only operates for 30 minutes, only 10,000 BTUs of heat energy will be removed. If the system operates for 2 hours, then 40,000 BTUs of heat energy will be removed, and so forth, so on. Some catalogs and specification sheets, the H or HR, may be omitted from the unit of measure and only the word BTU is used. When this is done, the BTU rating is to be assumed as per hour. Another term that you will hear often is to rate the capacity of the system is tons of refrigeration. Very important, especially on the air conditioning side of the fence. 1 ton of refrigeration is equal to 12,000 BTUs an hour. A 2-ton system therefore has the capability or capacity of 24,000 BTUs an hour. A 3-ton system has a capacity of 36,000 BTUs an hour. So if you take 1 ton of refrigeration, I believe that, and multiply it in a 24-hour period, that's 244,000 BTUs, which is quite a bit of heat. The term ton of refrigeration originates from the fact that 288,000 BTUs of heat energy must be used to melt 1 ton of ice over a 24-hour period. Since it makes more sense to work in hourly units, that figure is converted to 12,000 BTUs of heat energy per hour. 288,000 BTUs divided by 24 hours. So that's where we come up with the 12,000 BTUs. And it's very important when you're purchasing air conditioning equipment that you look at the heat gains and heat losses in each area of the house. As an example, room air conditioners are also sold in BTU ratings, and they basically, it can be 6,000, 9,000, 12,000, 18,000, 24,000, etc., etc. Now, if you buy a small unit and you're trying to cool off a room with a high ceiling and you have 5 or 10 people, a 6,000 BTU unit is not going to cut the mustard under any circumstance. It's extremely important you calculate how much heat is being generated on the room on the hottest day of the year. Energy consumption is also an important part of rating the system and its components. The energy efficiency ratio, EER, and the seasonal energy efficiency ratio, SEER, are ways of representing the energy efficiency of a system. Mathematically, the EER system is calculated by dividing its rated cooling capacity, measured in BTUs per hour, by the energy input measured in watts electric power. It's a very good process and it's very accurate. EER has been around for a long time. I will tell you this, in California, if you're going to put in a new split system or a package unit air conditioning system, 14 is going to be the magic number as far as the seasonal energy efficiency ratio. So the higher that number is on that yellow sticker, which is required by federal law to be attached to all cooling equipment, basically that means the less amount of power that is needed to make that process happen. Here's the formula. So if you have a 20,000 BTU per hour air conditioning system consumes 1,600 watts electrical power, its EER is 12.5, which is not bad. The equation is broken down like this. EER is equal to the cooling capacity divided, subtracting the energy input. Mathematically speaking, now we go to EER, 20,000 BTUs an hour, 1,600 watts divided, that equals 12.5. And remember, as this number goes up, that means less amount of energy required to make the system work, makes it more effective. The higher the EER, the more energy efficient the system is. SEER measures efficiently a cooling system operate over an entire season. So our air conditioning season here in SoCal typically runs from the end of May till the middle of October. So we're in the first week of September as I'm recording this lecture. We probably got another we probably have another 6 weeks before the cooling season is basically over. So as an example, we would compute the SEER based on the end of May till probably the end of October and rate the equipment accordingly. Another method, rating method, is the coefficients of performance, COP, which like EER is expressed as a ratio of the amount of heat removed from the system to the amount of electrical energy consumed. This time, both the output and the input is measured in BTUs per hour. To convert watts to BTUs per hour, you must multiply 3.413. Previous example, 1,600 watts is converted to 5,461 BTUs per hour. 1,600 equals 3413, and this coefficients of performance, COP, for the system is approximately 3.7. The equation is expressed as follows. COP equals BTU output over BTU input. So you divide one into the other. The 5461 BTUs 5461 BTUs per hour into 20,000 BTUs per hour, you come up with a number of 3.66. Notice that the coefficients of performance is determined by multiplying the EER times 0.293. In this example, 12.5 times 0.293 equals 3.66. Refrigerants. A refrigerant is a fluid that absorbs heat energy as it flows through the evaporator and then expels that same heat energy as it flows through the condenser. Although all fluids can absorb and expel heat energy, not all are suitable for use in a refrigeration system. In order for a fluid to be used safely as a refrigerant, its properties must be compatible with the equipment and with the range of temperatures and pressures normally assigned or encountered in that refrigeration system. Safety is one of the most important factors in the selection of fluid to be used as a refrigerant. Refrigerant must be safe for a service technician, for the equipment operator, and for the equipment itself, and for the environment. A refrigerant should possess a lot of other qualities. It should have the ability to mix well with its lubricating oil. It should have a low specific volume, and it should have a high latent heat factor. There are many types of refrigerants in use today. Last time I looked, there was over 80, probably closer to 100 now. Many are designed and used for particular applications. Some are used exclusively in medium temperature refrigeration systems, as an example, or low temperature systems, anything below 32 degrees. However, some refrigerants are more versatile. For instance, 134A, if you look at this figure here, is a popular refrigerant for medium temperature refrigeration systems. It's also used in low temperature systems and in automotive air conditioning systems. That's no longer true on the new cars. The new cars now have transitioned away from R134A. Now they're utilizing a product called 1234YF, is the new refrigerant for new automobiles. Be aware of that. Types of refrigerants. When designing a system, an engineer or service tech must choose the refrigerant whose properties are most compatible with the system components and with the application. Many factors must be considered. All properties of the refrigerant must be within an acceptable range. Even if one property is not within a specific range, it may be enough to make the refrigerant an unacceptable choice. This does happen occasionally. Properties of refrigerants. There are numerous properties that the design engineer or service tech must take into account when selecting a refrigerant for a particular application. Some of these properties include pressure temperature values at saturation, specific volume, toxicity, flammability, ozone depletion potential, global warming potential, stability and compatibility, miscibility, and latent heat factor. Pressure temperature values are expressed as a saturation temperature for the refrigerant. The pressure of the refrigerant at a given temperature and both when it's, a pressure of refrigerant at a given temperature when both its liquid and vapor forms are present must be within an acceptable range for use within the condenser and evaporator. If the pressures are too high or too low for the required temperature range, then the refrigerant is not a suitable choice. Good example of this, I do work for Amtrak cars occasionally, and private railroad passenger cars are used in a very limited way on scheduled Amtrak trains, as an example. Many of these old passenger cars use R12 refrigerant as a air conditioning refrigerant for the air conditioning system. Well, the problem with R12 is it's a CFC refrigerant which went away back in 1996, and it was phased out, and 134A replaced it. Well, some people got the idea, well, why not just take and put one, instead of having R12, which is no longer available, just put in HCFC R22 in replacing it. Well, that's a bad idea, and the reason why it is, the condenser has to be larger, the evaporator has to be larger, the metering device has to be different. You got all these factors thrown in there, and some of the private car owners did not take this into consideration when they were converting these old air conditioning systems to R22, which of course now is on its way out, is no longer manufactured here in the United States. Well, what am I saying? I've actually worked on a lot of air conditioning systems that were shoehorned, converted to R22, and it's very interesting in hot weather. They have a tendency to shut down, overheat, not cool the car down correctly. And I keep pointing out to these car owners that the problem is this: the refrigerant ability to absorb heat is limited because of the refrigerant that is now in use. In other words, R12 was replaced with 134A. If the car owners had made the choice to convert their systems to 134A, they could have gotten away with it. In this case, they converted their system to R22, thinking that they could absorb more heat in a dome car, as an example. Well, this has created more problems than it's solved. Properties of refrigerants, pressure temperature values at saturation. For example, the saturation pressure for R134A is 19 psig at a temperature of 21 degrees Fahrenheit and 135 psig at a temperature of 105 degrees Fahrenheit. This makes 134A a very suitable refrigerant for use in medium temperature refrigeration systems. On the other hand, R11, which has a saturation pressure of 21.08 inches of vacuum in a temperature of 20 degrees Fahrenheit, makes it a poor choice for use in a medium temperature refrigeration system. Damaging high compression ratios can result when low pressure vacuum, the low side pressure is in a vacuum. That's the reason why R11 is restricted to use for centrifugals. And don't forget, R11 is no longer made because it's a CFC refrigerant. When I got into this trade 45 plus years ago, I worked on a lot of chillers with R11. Basically, at room temperature, the refrigerant is liquid, and instead of in large pressurized cylinders, they were actually shipped in 100 and 200 pound drums. Quite interesting. Specific volume. Specific volume is the volume that 1 pound of refrigerant vapor occupies. It's advantageous as for a refrigerant vapor to have a low specific volume. Most refrigeration compressors pump a constant volume of refrigerant vapor per minute. The lower the specific volume of the refrigerant, the more refrigerant the compressor can pump. Toxicity. This is a big problem. Toxicity is the degree in which the substance is a toxic or poisonous compound. Obviously, the low toxicity is a desirable characteristic in a refrigerant. Accidentally inhaling small amounts of low toxicity refrigerant vapor should not cause any long-term health problems. Be aware that you may encounter toxic refrigerants in certain applications. Check your MSDS charts. As an example, R717 ammonia is often used in large industrial refrigeration systems because 717 is so efficient at transferring heat, its use is permitted. The health hazards associated with ammonia are addressed by special rules that limit its use and control how it's installed. Special care must be taken by technicians who work on systems that use toxic refrigerants such as ammonia. This includes personal protective equipment, PPE for workers, and special safeguards for the environment. The one thing I find is interesting about ammonia is it has no damaging effect to the environment in the form of ozone depletion or global warming. Here's a rather sore subject with refrigerants. The flammability properties. Flammability is the ability of refrigerant to support combustion. Refrigerants range from non-flammable to a moderately flammable to very flammable. Many of the more flammable refrigerants are no longer used today or used in such small quantities that are not dangerous. Some may be found in small quantities in special applications such as self-contained refrigerators or ultra-low temperature systems, or even mixed with other refrigerants to reduce their flammability. As an example, butane propane is part of the mixture of some of these new refrigerants that are in use. The idea being we want to try to get rid of the refrigerants that create global warming, and one of the things that they have done is increase the flammability by utilizing these different gases, in this case, in order to reduce the global warming or environmental impact. Ozone depletion potential, ODP. Scientists have proven that some refrigerants, when released into the atmosphere, chemically react and deplete the Earth's ozone layer. This was covered previously. ODP is a number derived to represent the refrigerant's relative ability to destroy the stratospheric ozone. The higher the number, the greater risk for damaging the ozone layer. CFC refrigerants have a high ODP number, and they went out in January 1996. HCFCs have a much lower ODP than CFCs, and HFCs have an ODP of almost zero. But what's interesting, HCFCs have basically been phased out now, R22 being a member of that family. Now, HFCs have been known to contribute to global warming, and as a result, a lot of them are on their way out now. So stay tuned. More refrigerants coming down the pipeline. Global warming potential expressed as the term GWP. Scientists also believe that certain refrigerants, when released into the atmosphere, are preventing the sun's long-wave infrared radiation from escaping, causing a gradual warming of the Earth's temperature. I don't think we need to argue about that. The GWP is a number derived to express how much impact the refrigerant will have on global warming potential. The lower GWP, the better the refrigerant is for the environment. CFC refrigerants have a very high GWP, and some HFCs and HFCs also have GWP numbers that are quite high. The more stable a refrigerant is, the higher its GWP. So you solve one problem, you create another. Stability and compatibility. Refrigerants should not break down under normal operating temperatures and pressures, nor should they react adversely with materials used in the system. One thing I want to say about refrigerants, I don't care what refrigerant you're using, as long as the refrigerant is contained, as long as the system is leak-free, it'll operate fine. It will not cause any damage to the environment as long as it remains in that condition. Where the problem lies is when people do a poor job of installing equipment or fixing equipment where leaks have occurred, then refrigerant basically is allowed to escape into the atmosphere and contribute to the climate change that we are currently experiencing. Miscibility. This is referring to the refrigerant should mix well with refrigeration oil utilized in a system at all expected temperatures. The ability of the refrigerant and lubricant to mix is called miscibility. Allows the oil to travel with the refrigerant as it circulates through the system and ensures proper return of the oil to the compressor. Remember, the oil is supposed to be in the compressor, but it travels through the condenser, through the liquid line, through the metering device, through the evaporator, and then finds its way back to the compressor. As long as the design is proper, pipe is pitched, sizing is correct. Now, the one thing I want to talk about miscibility on a quick note, we're utilizing POE oil now in all compressors, pretty much. We've eliminated mineral oil, we've eliminated alkylbenzene oils in new compressors. We found that POE is the oil of choice to make this happen with the refrigerants that are in use today. The downside to this is POE oil is like a sponge. It has the ability to absorb moisture anywhere. And for that reason, POE oil is never shipped in a plastic container. It's always a metal container. If you leave that container open more than 30 minutes, that oil has to be disposed of because it is no longer usable. The only way you're going to get moisture out of POE oil is to take and change the liquid line filter dryer, period. I don't care how good your vacuum pump is, it will not do the job. Latent heat or hidden heat. Heat energy required to change a liquid to a vapor or a vapor into a liquid is called latent heat. Majority of the heat energy picked up and released into a refrigeration system occurs through the process of the refrigerant changing state. As an example, from liquid to a vapor. Good refrigerant will have a high enough latent heat factor to minimize the quantity of refrigerant that must be circulated through the system. Chemical composition of refrigerants. Many of the refrigerants used today are carbon-based fluids. Carbon atoms are combined with other atoms in various configurations to form a variety of refrigerants. When carbon atoms are joined with chlorine and fluorine atoms, the result is a group of refrigerants called chlorofluorocarbon, CFC refrigerants, which have now been banned. When carbon atoms are joined with hydrogen, chlorine, and fluorine atoms, the result is a group of refrigerants called hydrochlorofluorocarbon, HCFC refrigerants. When carbon atoms are joined with hydrogen and fluorine, the result is a group of refrigerants called hydrofluorocarbon or HFC refrigerants. So basically your CFCs are gone. HCFCs are pretty much being phased out as we speak. There's still refrigerants in stock that for replacement use only, and not for new equipment. And HFC refrigerants are going to start being restricted next year in new equipment, and more refrigerants coming down the pipeline. More information to follow. Stay tuned. Individual refrigerants formed within each of these groups depend on the number of number of atoms combined, how they are joined, the molecular structure. For example, one atom of carbon is combined with one atom of hydrogen, one atom of chlorine, and two atoms of fluorine. The result is CH4, 1F2 as a molecule of a popular refrigerant, R22, which is classified as an HCFC refrigerant. Might add, there's millions of air conditioning systems in the United States. They still operate off of R22 or HCFC22. If two of the atoms of carbon are combined with two atoms of hydrogen and four atoms of fluorine, the result is a CF3CH2F is a molecule of another popular refrigerant known as 134A, which is an HFC refrigerant. This is the molecular structure of R134A, carbon atom, fluorine, and hydrogen. Refrigerant classifications. Refrigerants are classified not only by their chemical composition, CFC, HCFC, or HFC as mentioned above, but several other ways as well. For an example, refrigerants can be classified in the evaporator temperature as follows. High temperature applications, usually between 45 and 60 degrees Fahrenheit. Medium temperature applications, usually between 28 and 40 degrees. Low temperature applications between 28 and -5 degrees. Ultra low temperature applications between -5 and -40, or ultra low temperatures below -40 degree Fahrenheit. Now, why would you have something that cold? I would give you an example. I was in the U.S. Navy, and one of the things we had on our ship was what we called an O2 N2 plant. Utilized R22 as a refrigerant. That particular plant basically had the ability to taken for us as a ship to bottle nitrogen. So, by taking it at a critically low temperature, we could separate the oxygen from the nitrogen and bottle it for use on the ship when we were deployed. Refrigerant classifications. R401 alpha is a refrigerant typically used in medium temperature applications. I would dispute that in new applications currently in use. Many refrigerants can be used in more than one type of application. R22, as an example, typically used in medium high temperature applications, also be used in low temperature applications. I personally don't like R22 in low temperature applications because of the higher pressure, temperatures, problems with oil carryover. I've worked on systems containing R22 in low temperature, and I will tell you this from years of experience, it's a pain. It's a royal pain. The reason why R22 was selected was when the CFCs went out of production. Some people took the cheap way out and used R22 to replace it, which turned out to be a very bad decision instead of using some of the alternative refrigerants that were available at the time. Refrigerants are also classified according to their toxicity and flammability. Each refrigerant is assigned a letter A, B, C for toxicity and the number 1, 2, 3 for flammability. Look at a safety matrix, which is shown on figure 2-9 on the next slide. As you can see, a Class A refrigerant has a low toxicity rating, whereas a Class B refrigerant has a higher toxicity rating. As for flammability, Class 1 refrigerant has no flame propagation. A Class 2 refrigerant has a low flame propagation, and a Class 3 refrigerant has a high flame programmation. So here's that chart that we talked about from the previous slide. You're going to see this a lot when classifying refrigerants. Basically, if you look here on the left side, this is your flame characteristics. Increasing flammability is going to be reflected on this side of the chart. Toxicity is going to be from this side here, from A1 to B1, A2 to B2, A3 to B3. So basically, if you have a B3 refrigerant, you got a higher flammability, plus you have a higher toxicity to deal with. I doubt if you're going to find any refrigerants that are in current use with this classification in place, but I could be wrong. Refrigerant classifications, the toxicity, flammability ratings are typically combined to designate the overall safety of the refrigerant. Refrigerant with an A1 classification is very safe refrigerant, both in its toxicity and flammability ratings are very low. Refrigerant classified as a B3, on the other hand, is very unsafe, both in toxicity and flammability ratings are very high. I would say that butane or propane, which is a fuel source, would fall under this category. Refrigerant blends. When two or more refrigerants are combined to form a new refrigerant, the result is called a blend. Many of the blended refrigerants are either binary, a mixture of two different refrigerants, or a ternary blend, a mixture of three or more refrigerants. Refrigerant blends are classified as azeotrophs, xeotrophs, or near azeotrophs. Azeotrophs are a blend of two or more single component refrigerants with a common boiling point that occurs at one specific temperature. Composition of a blend remains at near constant as the refrigerant changes state. Refrigerants in the 500 series such as R500, R502 are classified as azeotrophs. And by the way, those two refrigerants, R500, 502, are in the CFC class, which went out of production January 1st, 1996. You will not find them around. Xeotrophs is a blend of two or more single component refrigerants with different boiling points. Under certain conditions, the xeotroph can experience a fractionation, which is a change in the composition of the blend if a leak occurs. Fractionation occurs because components that make up the blend evaporate and condense at different rates. This could definitely be a problem if a leak occurs in the system. Xeotrophs mean the refrigerant goes through a range of saturation temperatures as it changes state from a liquid to a vapor or from a vapor to a liquid. The difference between the starting and ending temperatures of the refrigerant phase change at a constant pressure is called the glide factor, which can vary as much as 16 degrees Fahrenheit. Xeotrophs. You should be familiar with the following terms. Bubble point, that's the term we're going to use when we're doing subcooling with a blend refrigerant. The temperature which the last refrigerant vapor is condensed as heat is removed from the blend, used for calculating subcooling. Dew point is the temperature of the last liquid refrigerant as it's evaporated, heat is added to the blend, and this is used for calculating superheat with refrigerant. R401 as an example and R407C are classified as xeotrophs. 407C is a widely used replacement refrigerant for R22. The problem with R407C, it is a blend. It must be charged as a liquid, not a big deal there, but you cannot mix 407C with R22. If you have a system you're converting from R22, you got to take the remaining R22 out, and then in some cases change the oil in the compressor before converting it over to 407C. Near azeotropes. Near azeotroph is a blend that is technically a xeotroph, but acts more like an azeotroph. A little bit confusing. That is, it behaves like a single component refrigerant, which it isn't, showing a minimal amount of glide, less than 1 degree at normal operating temperatures, and a very limited amount of fractionization. R410A as an example of a near azeotroph. Near azeotrophs, note, because the components of an azeotrophic mixture will not separate under normal operating conditions, an azeotroph may be charged as a vapor or as a liquid. Xeotrophs or near azeotrophs, on the other hand, must be charged in a liquid state to ensure proper mixture composition. So what this slide is saying is if you have R4010A, you could charge it as a vapor, but in practice, we always charge it as a liquid, but we throttle off that liquid going into the low side of the system so we don't create damage. Typically, we are going to add liquid after the system factory charge has been open to the rest of the system and the unit operates for a period of time in order to get our subcooling to the correct charge level. Refrigerant identification. Refrigerants can be identified from a variety of ways by their ASHRAE, ANSI/ASHRAE designations, molecular formulas, manufacturer trade names, or by the color of the cylinders. There's a move afoot to basically standardize the color of all refrigerant cylinders because there's so many refrigerants out there and there's not enough colors in the rainbow, I guess, that can identify each and every refrigerant blend that's available now. They're talking about standardizing the color to probably a yellow-gray and then identifying the refrigerant by stamping the ASHRAE number, letter number designation. More to follow. Refrigerant identification. As a technician, you will become familiar with all these methods. The ANSI ASHRAE designation is probably the most common way referring to refrigerant. It consists of the R, which stands for refrigerant, followed by a number. R, of course, stands for refrigerant. The number following the groups of refrigerant according to its base compound used in making that refrigerant. For example, the 00 series of refrigerants numbered from 1 to 99 are methane-based compounds. R22, which is a common refrigerant used in many air conditioning systems, is in the 00 series of refrigerants. The 100 series refrigerants from 100 to 199 are ethane-based compounds. 134A is a new refrigerant commonly used refrigeration system, is in the 100 series of refrigerants. Sometimes you'll see R replaced with the acronym identifying the refrigerant's chemical makeup, CFC, HCFC, or HFC. As an example, R22 may be referred to as HCFC22, or R134 alpha is referred to as an HFC 134A. Refrigerants can also be identified by their chemical names. Chemical name for R22 as an example is dichlorofluoromethane. The chemical name for R134 is 1112-tetrafluoroethane. Obviously, the scientific naming system is a difficult way for most of us to identify refrigerants, and it's very seldom used. Many refrigerant manufacturers use the trade names to identify their products. For many years, DuPont used the trade name Freon. Everybody knows Freon, and that is it's kind of funny today. People say, "Well, are you going to change the Freon in this system or check the Freon?" Everybody knows the term Freon because DuPont marketed this thing for years and years and years. The problem is Freon is a trademark of the DuPont Corporation. Okay, so Suva is also a name that DuPont's given to a new group of refrigerants designed to replace phased-out CFC refrigerants, which I think are now also on their way out. Other manufacturers use trade names to identify a single component, like Icor. Manufacturer of R414B uses the trade name Hotshot. There are so many names out there, it's frankly hard to keep track of all this stuff. Refrigerant identification. Refrigerant cylinders are also color-coded so that the person can easily identify a refrigerant by the color of the cylinder. For an example, R22 is shipped in a light green cylinder, R134A is a light blue cylinder, and R410A is a deep pink cylinder. As phase out of CFC, CFC, HCFC, and HFC refrigerants continues under Montreal Protocol and the other succeeding documents. Alternative refrigerants that have a zero ozone depletion potential and a low global warming potential are being introduced into the refrigeration equipment worldwide. In some cases, some refrigerants that are used in the late 1800s and early 1900s are being reintroduced in a variety of applications under controlled conditions. As the Environmental Protection Agency and other government agencies introduce these alternative refrigerants, it's essential for technicians to become familiar with the new refrigerants and receive additional training on related handling, transportation, installation, servicing, and equipment design issues. Such training programs, as an example, RSCS publication, Hydrocarbon Refrigerants, developed specifically for the industry, address the important safety concerns and help ensure compliance with codes and regulations in existence. Some of the more commonly used alternative refrigerants approved for various applications, equipment types, capacities, and charge quantities include hydrocarbon HC refrigerants such as R170 ethane, R290 which is propane, R600 alpha which is isobutane, and R441 a hydrocarbon blend which is permitted for retail standalone food refrigeration, vending machines, as well as household refrigerators, freezers, and room air conditioners. Ammonia 717 is experienced expanded use in applied commercial industrial equipment. The reason being because this is a cheap refrigerant and it does not create any damage to the environment. Carbon dioxide, or CO2, R744 is used as supermarket refrigeration and process equipment operating either with a transcritical or subcritical refrigeration cycle. Hydrofluoroethene, HFO, refrigerants such as HFO-1234YF is proposed for automotive. That's in use now. Some hydrocarbons, hydrofluorocarbons, HFCs, with low global warming potential such as R152A, automotive, and R32, room air conditioners, and possibly residential, light commercial AC and heat pumps. One thing I got to say at this point, when you are working on newer equipment, you must pay attention to the label. You cannot assume that a particular refrigerant is charged into the system that you think has been there for years and years. As an example, you may have a room air conditioner which you think has R410A in, when in actuality it might actually have R32. So please pay attention to the labels from the manufacturers. The law requires that all equipment manufactured for the heating, cooling, as well as refrigeration industry has to label the refrigerants that are used in that process. Again, the use and application of these alternative refrigerants will require additional training, since these refrigerants may be more flammable and or more toxic, may operate at higher pressures, may have limited use applications, and may have different charge allowances than the systems on which most technicians are accustomed to working. It's important to realize that the systems with these refrigerants are OEM designated, designed, and UL approved equipment only. Alternative refrigerants. They are not designed as drop-in, retrofits, or change-out refrigerants for existing systems. Please take a note of this. EPA guidelines govern which refrigerants must be recovered, which refrigerants can be vented. In most cases, HC refrigerants can be vented directly into the atmosphere in limited amounts. Interesting. Be sure to consult EPA regulations. They are frequently updated and revised if you're working with alternative refrigerants. In other words, folks, please stay informed. Refrigeration oils. Bearing surfaces inside a compressor require lubricating oil, but not just any oil can be used. The oil needs to be specifically designed for use in refrigeration systems. Oil must possess certain properties that make it compatible with components of the refrigeration system in which it operates. If you look at those samples of oils illustrated in that slide below, You will not see the oil that is currently used in new compressors. It could be an alkyl benzene, it could be mineral oil, which has been phased out for the most part in new equipment. And as I said, POEs are always stored in metal cans. Oil must not break down under normal operating temperatures to which it is exposed. It must mix and travel well, miscibility once again, with the refrigerant in the system, and it should not react with any components in the system to form harmful byproducts. Refrigeration oils. There are currently 4 types of oils commonly used in refrigeration air conditioning systems. Mineral oil, which is pretty much being phased out. Alkyl benzene oil is still in use. POE is in wide use, and polyvinyl ether, PVE. I've not seen that. This type is selected depends on the refrigerant used in the system. Since the oil travels with refrigerant throughout the system, oil and refrigerant must mix well in order to ensure that oil returns to the compressor. Please note that not all refrigerant oils mix well with refrigerants, although some refrigerants are compatible with more than one type of oil. The design engineer and the service technician must make sure that the oil in the system is matched to the refrigerant for use in the system. Properties of refrigerant oils, refrigeration oils. Some of the important properties of an oil that enables it to be used as a lubricant air conditioning system, refrigeration systems are the viscosity, the flock test, the dielectric strength, the neutralization number, flash point, and fire point. Let's talk about viscosity. The properties of refrigeration oils. Viscosity refers to how thick or thin the oil is at a given temperature and how readily it flows at that temperature. The oil becomes more fluid as it flows more easily as the temperature increases, and the more viscous, thick at low temperatures. If the oil becomes too thick, it may become too hard to circulate throughout the system. Flock test. All mineral oils contain paraffin wax, some more than others. Even those that are so-called wax-free contain very small amounts of wax. The flock test determines the temperature at which the wax separates from the oil. The value should be low enough so that wax will not settle out of the temperature encountered with the system. Dielectric strength. Dielectric strength deals with the resistance of oil to electric current. It is important for the oil to have a high enough resistance to prevent the conductance of current and voltages applied to the compressor motor, such as hermetic compressors. Neutralization number. The neutralization number represents alkaline and acidic levels of refrigeration oil. A new refrigeration oil should never contain mineral acids. A low neutralization number indicates the absence of corrosive mineral acids. Flash point and fire point. The temperature at which the oil vapor at the top of the oil will burn if a small flame is presented, which is called flash point. The fire point is the temperature at which the oil will ignite and continue to burn. Refrigerant oil mixture. Oil pumped from the compressor must be returned to the compressor, otherwise it will seize up. Otherwise, the compressor will lose its oil charge, bearing surfaces will not be lubricated, and the results are a seized up compressor. When the refrigerant is in its liquid form, the refrigerant and the oil mix very well together. Oil has no problem moving along with the liquid refrigerant. However, the refrigerant is not always in its liquid form. When the refrigerant's in its vapor form, it may not mix well with the oil. Refrigerant oil mixture. Gravity is one way of returning the oil to the compressor, but in order for the gravity to be used, the refrigerant lines that carry the vapor must be pitched back towards the compressor. Piping practices must be correct. This is not always practical since some lines can be pitched back and some cannot. Because gravity alone will not always be counted on to return the oil to the compressor, another approach is the use of velocity of the refrigerant vapor to sweep the oil back to the compressor. Generally, the velocity of refrigerant vapor must be over 1,500 feet per minute. when traveling through a vertical riser and at least 750 feet a minute on horizontal pipe runs. Leak detection. Systems of refrigerant leaks are costly to the owner of the equipment and can be harmful to the ozone layer. Before utilizing any tool to search for a leak, a technician should perform a simple visual inspection of the equipment. Since oil is mixed with refrigerant, travels through the system with refrigerant, trace amounts of oils will leak out along with the refrigerant. Oil leaks are the easiest to find in a refrigeration air conditioning system. Oily spot on a pipe or some component is an excellent location to begin looking for a leak. And this doesn't require any equipment, just the use of your eyesight. There are several devices and methods that technicians can use to locate leaks, including soap bubbles, electronic leak detectors, my favorite ultrasonic, which uses sound waves for leak detection, injected refrigerant dyes, talked about that previously, halide torches, that is considered an antique practice, I would not use it, and the approach you choose will depend on the size and location of the equipment and or on the tools which you have available. One of the oldest, simplest means of detecting a leak and still popular, especially in small systems, is a soap solution. Placing a pre-formulated solution like the one shown in the illustration below on this slide, suspect area will reveal if there's any leak present or not. If the solution bubbles, then there's a leak. Now, one thing you got to be careful about, there are some soap bubble solutions that contain petroleum solvents. They should never be used with oxygen, because the petroleum mixed with oxygen can cause an explosion. Please read the manufacturer's MSDS sheets before purchasing this type of soap solutions. This doesn't happen very often. Most of the soap bubble chemicals are compatible with different gases, including refrigerants, when doing leak detection. What I happen to love about the ultrasonic leak detection method is you don't put liquid on anything, and basically you're taking the sound, basically a microphone, and listen for a change in the noise level at a suspected leak area. And once you start utilizing a ultrasonic leak detector, utilizing headphones, I can pretty much tell you you'll never go back. Those things work great. To use this method, there must be a measurable amount of pressure inside the system, either pressurized with refrigerant or dry nitrogen. While this is not an efficient way to find a leak in a large system, it can be used to help pinpoint a leak that is found by other methods. Typically, that's what I do in my practice. I will utilize a electronic leak detector first, and then I will follow up with soap bubbles. Another method that's common is use electronic leak detector. As an example in the slide below, sample of the air is drawn across the sensor inside the leak detector. If refrigerant is detected, the leak detector will send out an audible or visual signal, such as a series of beeping sounds or flashing lights. I can also tell you those tips have a tendency to become contaminated. Okay, this one, system pressure does not have the ability of an ultrasonic leak detector to find leaks, since the device responds to sound. The ultrasonic leak detector is illustrated down below. Is very sensitive instrument capable of detecting the sound of leak producers. These things work. I will tell you that. I personally own one of these. I highly love it. And especially with 410A leaks, this thing is foolproof. This particular unit here does not have a sniff tube that mine does. Mine is an AccuTrack system, and it works extremely well. Glad to demonstrate it to you if you request it in the lab. When refrigerant escapes through a leak opening, it creates an ultrasonic sound to the human ear. It can only be detected if the leak is large enough and the background noise is not too excessive. For that reason alone, you have to wear earphones. Small leaks, the sound of a leak may fall outside of the audio frequency of the human ear. But I will tell you this, all the places I've used this leak detector, I've not had that issue. But if you have a lot of background noise, such as a machinery room, that's going to be a problem. I will tell you that for a fact. An infrared leak detector, which I also own, one made by Fieldpiece, is on this slide, can detect CFC, HFC, and HCFC blends and work on the principle that refrigerants reflect a certain spectrum of light. The IR detectors detects the changes in the concentration of refrigerant, then the absolute concentration of the refrigerant. This enables them to detect leaks in locations where refrigerant may be present in the air. These things work very, very well. They're very easy to use, and they do a good job. But the thing is, patience is the key. When you're using these leak detectors, patience is the key. If you're an impatient person, you are going to struggle with this technology. I will tell you that. Refrigerant dyes can also be injected into the system. I talked about that previously. These dyes mix with refrigerant and oil in the system. When they leak out with the escaping refrigerant, they stain the area so that the technician can easily locate them using infrared lighting. Most dyes are now fluorescent and can be seen with a black light. Work very well. The Halide Torch is an older device used to locate leaks. This type of leak detector can only be used with CFC and HCFC refrigerants that contain chlorine. So frankly, this thing is useless in today's refrigerants. The flame in Halide Torch normally burns blue in color, and in the presence of the CFC, HCFC refrigerants, the flame will turn to a green in strong concentrations. Small air sample is drawn through a tube and directly into the flame. Refrigerant is present. Blue flame will turn greenish color and result in chlorine being burned off. Now the bad news about this leak detector is if you have a large quantity of the refrigerant being sniffed, you're basically going to create phosgene gas, which obviously is hazardous to your health. Obviously, drawback to the Halide Torch is the hazard of using open flame in a confined space. In my opinion, this thing is a museum piece, and that's all I'm going to say. Because some refrigerants, some refrigeration oils are highly flammable because of toxic and corrosive gases can be produced with refrigerants and lubricants are burned. The use of halide torches for detecting leaks has been banned by many codes and regulations. Once again, we don't use them anymore. Replacing refrigerants and oils. Since the phase out of CFC refrigerants, new refrigerants have been developed to replace them. However, as previously stated, none of the new refrigerants are a drop-in replacement, since the new refrigerant cannot simply be added to existing refrigerant. The baseline record of equipment must be established, the old CFC refrigerant must be removed from the system, the filter dryer replaced, the system evacuated, and the replacement refrigerant added to the system following recommendations of both refrigerant and equipment manufacturers. I will tell you this, you're going to come across a lot of R22 equipment that is older in nature, typically 20 to 30 years old. It is frankly better just to change out all the equipment than try to convert to another alternative refrigerant because of the age of the equipment. I always tell my customers that retrofitting no longer makes sense. There are a few cases where a coil was changed out 5 or 10 years ago and will accept it'll accept like R410A as an alternative refrigerant. I have made those conversions, which are relatively easy, but from a energy efficiency standpoint, from an environmental standpoint, frankly, if you have an old R22 system, it's just better to recover the refrigerant and scrap the equipment. End of discussion. Depending on the replacement refrigerant selected, the refrigeration oil may also need to be replaced. Always make sure the oil and the new replacement refrigerant are compatible with each other and the correct minimum percentage oil mixture of oil of the new oil charge is achieved. Once again, taking a compressor out of a 20-year-old system and changing the oil to, say, as an example, POE is a royal pain. I'm just going to tell you that. I have done that many, many years ago. I no longer do that. If the system requires a refrigerant change, you're just better off to price up new equipment that already has the new compressor with the proper oil that will accept a refrigerant such as R410A. Replacing refrigerants and oils. Other changes may need to be made to the system when the refrigerant is changed. The pressure control, the metering device, any pressure regulators or safeties, all these may be adjusted or replaced as needed. Gaskets, seals, O-rings may also need to be replaced. Once again, if the equipment's old, my advice to the customers is always just to replace the equipment. Replacing refrigerants, oils, again, technician must look at the whole picture before changing refrigerant and take the steps necessary to make sure the job is completed correctly. Depending on how much additional expense is involved, you may need to calculate whether it's worth converting the equipment. In most cases it's not, or whether it's more cost effective to put new equipment. I would say that's usually the case. The problem is, in our current COVID economy, the new equipment may not always be available, and that is a big problem right now. Commercial refrigeration systems. There are several different ways classifying refrigeration systems. You may hear someone refer to a high temperature system, for example, low temperature system. These classifications are typically based on evaporator temperature, which is normally 10 degrees to 15 degrees below the actual case temperature. Various classifications include high temperature applications, evaporator temperature between 10 and 55 degrees, air conditioning as an example. Medium temperature applications has evaporator of minus 5 degrees to 25 degrees Fahrenheit. Low temperature applications has evaporator temperatures of minus 40 degrees to 0 degrees Fahrenheit. Extra low temperature systems, which have an evaporator temperature minus 50 degrees to minus 20 degrees Fahrenheit. Ultra low temperature systems has evaporator temperatures but minus 120 to minus 50 degrees. Systems that have evaporators below 120 degrees Fahrenheit are not covered in this chapter at all. Systems may also be classified as self-contained or built up. Self-contained systems, sometimes referred to as a package system, are those systems that are completely assembled at the factory by the manufacturer and require only electric power to start up the system. Built-up refrigeration systems must be field installed. Installing contractor pipes everything together, the individual components of the system, evacuates the system, and charges it. A system can be arranged in many different ways. For an example, a compressor condenser can be installed in a location distance away from the evaporator from metering device. This arrangement is commonly referred to as a split system. You'll deal with this in air conditioning, residential, and commercial a lot, as well as mini splits. Compressor condenser coil are often contained in a single condensing unit, which may be located outdoors or indoors or up on a roof. Another type of installation, the compressor is located indoors and the condenser coil is located outdoors. I've seen that as well. This arrangement is typically referred to as a remote condenser. Food service equipment. Refrigerated food storage units can also be divided into groups as follows: reach-in refrigerators, freezers, walk-in refrigerators and freezers, storage warehouses, and specialty equipment. So, reach-in refrigerators and freezers, walk-in refrigerators and freezers, storage warehouses, specialty equipment. Here's an example of a reach-in box used in the food service industry. They're manufactured either single door One compartment, the door can be installed in either to open left or right, or as a multiple door cabinet with several compartments. Some are even designed for under-counter use. Storage capacity is typically 5 cubic feet to 700 cubic feet. Care must be exercised locating the unit where the floor offers adequate support, since the units can weigh over 3,000 pounds in some cases. Adjustable legs are usually furnished to make it easier to level the unit. Leveling ensures that the condensate is drained properly. The evaporator's condensate line normally run to the floor drain or to a heated pan. The pan can be heated either by the discharge of the compressor or by a separate electric heater. When the discharge line is used, it helps reduce the discharge line temperature, which de-superheats the refrigerant. Freezer models must have the condensate line heated as well, so to prevent the condensate from freezing inside the lines. Some reach-in cases are self-contained systems that the condensing unit is located either on the top or the bottom of the cabinet. Others are split systems with condensing unit located either outdoors in a remote location of the building. There are advantages and disadvantages of both designs. Self-contained systems can be relocated easily, whereas remote systems must be repiped. Self-contained systems reject heat into the store, which is an advantage during the winter, but a disadvantage during the summer or into water. Food service equipment, walk-in coolers, freezers like the one shown in figure 2-17 down below. Another type of commercial refrigeration equipment. Walk-in coolers are typically made with modular metal-clad insulated panels, usually 1 to 4 inches thick, depending on the temperature requirement inside the cabinet. Usually these are designed as a knockdown type of construction where they're assembled like you would build a house. These are insulated wall sections that are modularly locked into place, and a floor and ceiling are installed with refrigeration equipment. Walk-ins are usually assembled on the job utilizing special eccentric cam fasteners. Insulated panels can also be used for the floors. The interior surfaces of the wall and ceiling panels are ordinarily clad with aluminum. Floors are typically heavy gauge aluminum or galvanized steel, but can be made with almost any finish desired. Because a substantial amount of heat needs to be rejected, almost all walk-ins are split systems and have to be assembled out in the field. A subset of walk-in coolers are called walk-in or step-in coolers. They are smaller, they have walls and doors that need to be assembled. But once the packaged refrigeration unit is installed, it only needs to be plugged in to work. Every time the door of the walk-in is open, warm air enters the case. To minimize the amount of warm air entering the case, some systems have a door switch that shuts off the evaporator fan when the door is open, especially for freezers. The door switch may also control the liquid line solenoid, which stops the flow of refrigerant to the evaporator. In some cases, the door curtain may be installed to further inhibit warm air from entering the cooler. The condensate line from the evaporator is normally piped to a drain outside the cabinet to a floor sink as an example. Condensate line should be sloped 1/4 inch per foot for proper drainage and should be individually trapped outside the walk-in to prevent outside air from entering the cabinet. If condensate lines are exposed to temperatures below 32 degrees Fahrenheit, such as the inside the freezer or low ambient location, they must be heated. Drain line heaters can be energized at all the time or be thermostatically controlled so they de-energize when they're not needed. Some self-regulating heaters do not require a thermostat to control their temperature. Cascade systems. When very low evaporating temperatures are called for, the basic vapor compression cycle must be enhanced to achieve the desired results. A single system cannot economically achieve the high compression ratios necessary to obtain the evaporating and condensing temperatures required. However, multiple systems can be joined and work together to achieve the desired results. The evaporator of one system is used to cool the condenser of the second system. This design is referred to as a cascade system. The heat exchanger on the interconnecting systems, which utilize both the condenser and the evaporator, called a cascade condenser. See figure 2-18 on the next slide. Cascade arrangement. Individual systems may utilize different refrigerants, each with a progressively lower boiling point. This allows very low evaporating temperatures to be achieved. This is an example of a cascade system here. Many years ago when I first started teaching these classes, this is something I really specialized a lot in. And if you look at, you got compressor A, compressor B. Notice that you have an interstage heat exchanger for the cascade condenser. You got condenser alpha, and you got condenser Bravo or B, and you have evaporator A and then evaporator B. And notice that both of these have oil separators, which indicate that this is an ultra low temperature system. Oil recovery is extremely important here. Cascade system offers some distinct advantages. Since each stage can be used a different refrigerant, it's possible to select a refrigerant that is best suited for a particular temperature range. Very high and very low pressures can be avoided. Migration or lubrication oil from one compressor to the other is prevented since the stages are piped independently from another. Another type cascade system which utilizes a compressor but multiple refrigerants is called auto cascade system. Using one compressor instead of 2 or 3 provides significant cost savings. The refrigerants have a greater boiling point, such as R404 alpha with a boiling point of -52 degrees Fahrenheit, and R23 with a boiling point of -116 degrees Fahrenheit are mixed together. Technically, this is a blend with several evaporators. Sometimes 5 or 6 refrigerants are combined to obtain colder temperatures. Okay, I believe this ends the lecture. These is the review questions for all the 5 chapters that we've, the previous lecture that we've recorded. These questions need to be completed and answered, and you have the ability to find out what the correct answer is by pressing the key after the proper selection has been made. So as in this example here, the 5 basic components of every vapor compression refrigeration system. So the best answer for this one would probably be the letter B. Notice that the red indicator shows a refrigerant, evaporator, condenser, or metering device. So please complete all these questions pertaining to this lecture, and thank you for your participation.